Hi, everyone. Welcome to the third lecture of Intro to Movement Neuroscience. Thank you for joining me today. I will be posting more information on how the tutorials will work, as well as the breakdown of the midterm shortly after this lecture today. Before we get started, is there any questions in relation to the material from the asynchronous portion of this lecture? No questions? Awesome. Excellent. Now, I must be honest with you that I find that this lecture is probably the driest of the lectures for this course. But if you remember from the intro lecture, when we talked about the different levels at which you can learn neuroscience, you basically have to start from the ground up. We learned the anatomy, and now we're going to be starting to understand neuroscience at a molecular level. None of the science should be difficult. I think that the main thing to understand from this lecture is the sodium-potassium pump, which I feel you have all, and I asked you the first day, I feel you all have some experience with learning the sodium-potassium pump, no? Perfect. So let's start off with the lecture. We went through all of this on the asynchronous portion, and I believe where do we start off? Here? Memory channels? Because she's a little bit rusty on it, but don't worry. We'll shine you up. Oh, not sharing. Oh, well, there you go. Thank you for letting me know about this. I will start sharing right now. It's funny that we're starting off on memory potentials because you all have a lot of potential. Remember that the point of the neurological system is just to send a signal from one area of the body to another. And then the way that your body has developed or evolved a way to do that is through the generation of electrical potentials. It's through putting ions on one side to another, you get like sort of an electrical charge or potential. And that's something that counts as energy that can be sent to different areas. And so the basis of our ability of the neuron to signal is through the development of electrical potentials. And all of that is occurring through these minute molecular changes in membrane channels. And so this is what I'm basically saying. Sorry, I forgot to hit next. There are four main channels that our neurons utilize to develop and send this electrical potential afferently or efferently throughout the body. The four channels are leak channels, modality-gated channels, ligand-gated channels, and then voltage-gated channels. Gated means that they open and close, whereas the leak channels are just always open. With channels, and I don't know if you remember this from A and P, but the channels are in the membrane. The membrane is what separates the intracellular from the extracellular space. Channels are an opening, but they're very specific to only one ion. So channels will only they're shaped in a way that they will only let one thing in and out. Leak channels are just constantly open. And there's leak channels that act as buffers throughout the entire neuron. Because the sodium-potassium pump that we're going to review in the next 5 slides is constantly changing the concentration of ions in and outside of the cell, the leak channels are there to always allow for some flowing at a slow, continuous rate, just in case. It's like a buffering system, just in case. So leak channels are constantly open, and they're there as a buffering system. The gated channels are what are really important in this generation of a electrical potential, and ultimately the transmission of that potential through a buildup of local potentials, and then ultimately an action potential down to the presynaptic terminals, or the end of the neuron. Like I had mentioned, there are 3 different gated type channels that we're going to learn about today in this lecture. Joseph has a question. So leak channels are not specific? Yes, they are. Yeah. Leak channels would be specific to different types of ions. But for the purposes of this lecture, I'm not saying, okay, there's this one for this ion, there's the one for this ion. There's just a multitude of different leak channels that are there to buffer out the buildup or excessive buildup of ions in the intracellular space. Yeah. The 3 types of gated channels that we're going to discuss today are the modality gated channels. Modality gated channels are going to be those channels that are on the sort of the dendrites of our sensory nerves. So we have sensory nerves that are going to be specific for temperature, for pressure, for vibration, for proprioception. All of those sensory neurons, they start with modality-gated channels on their dendrites. And these channels are going to be opening in response to a specific sort of sensory or mechanical force. So touch neurons are going to have modality-gated channels that are specific for touch. So when you touch, it's going to cause the channels to open and then ions to enter. Temperature ones are going to be specific for temperature changes. Chemical, so like pain is the sensation of pain is a chemical, and there's a breakdown of cells in the body. Your body perceives that as pain. That would also be sort of a modality-gated channels on the end of the sensory nerve. Ligand-gated channels, ligand just means like key, lock and key mechanism. Ligand-gated channels are going to be those channels that open in response to a neurotransmitter or a protein binding to it. So if sensory neurons have modality-gated channels on the dendrites of them, the motor neurons and the interneurons, because they are second in line, they're going to have ligand-gated channels on their dendrites. So they're going to open in response to neurotransmitters or different proteins that would act like a lock key mechanism. So when we're going to learn about the synaptic cleft, or synapses where neurons attach to each other, one neuron sends a neurotransmitter over to the next neuron, and that neurotransmitter is going to bind with the channels on the secondary neuron's dendrites. Those are really just ligand-gated channels, or channels that are opening in response to a specific protein. Yeah, so because the majority of neurons in our body are interneurons and motor neurons, then you could say that the majority of neurons have ligand-gated channels. Voltage-gated channels are the next one that we're going to discuss, and voltage-gated channels are in the axons of all neurons. It's the voltage-gated channels that are responsible for the action potential. Modality, sensory, ligand, motor, correct. Yep. And then so Shane is saying, just to kind of break down, modality means sensory, ligand, channels, motor, and interneuron. Voltage-gated channel, all of them. Is everyone okay with that? Perfect. And it's saying a voltage. Yeah. No. Yeah, that's true. Like in the action potential. So we'll get into that, but that's what it's for. So voltage is not ion specific, but charge specific. Yeah. So what happens is the voltage gated channels open up in response to a specific charge, and when they open up, they let in calcium or sodium and potassium. So here I have an example of a channel opening and closing. Would the voltage leak as well? I would say no. There's always some loss of electrical potential, but not for the purpose of this course. Are we all okay with the understanding of this idea of potential energy? I don't know if you all took physics or know of physics, but you know, if you like hold something up away from the ground, it now has gravitational potential energy, meaning that if I let go, it's going to fall. If you build up a charge and then you let go of what's holding the charge in, the channel, that charge is an energy. It's going to go somewhere. That's the concept of how action potentials are generated, and we're able to sort of send signals across our body. Does that make sense, everyone? I don't know if I scrolled up. Oh, Shane knows how to calculate it. Perfect. You won't have to calculate anything in this course, but feel free to do so. Maybe you can calculate your grade. The three different sort of electrical potentials that we're going to see, so the three different states we're going to see in the neuron. And remember, the point of today's lecture is to understand at a molecular level how the neurons work. We're going to have three different potentials that are possible, and through this is how we get our cell signaling. The resting membrane potential is probably something that you are all familiar with. It's the general potential that's created by the sodium-potassium pump. So it's the resting charge of the neuron. The local potentials are going to be those potentials that are generated at the dendrites. Shane, sensory, which ones are they going to have? Okay, and perfect. And then Hera, what about the motor and interneurons? What types of channels are they going to have on their dendrites? Perfect. Yep, Ligand. Okay, awesome. Learning, hashtag learning. Then on, for who wants to do next, for action potentials, what channels are responsible for that? Voltage. Yeah, there you go. Perfect. Voltaire. Here we have sort of a slide just depicting the resting membrane potential. So we have our sodium-potassium pump. The sodium-potassium pump is involving these channels right here. And the sodium-potassium pump is a protein that, in response to the use of energy, will pump 3 sodium out of the cell and 2 potassium in. So there's a net loss of a positive ion. And that is what's going to be developing our electrical charge. Here we have some leaks channels. So then, remember, Joseph, you were asking about, are the leak channels open to everything? No, there's actually ones that are specific for each ion. Michaela, which part?
Could you just repeat how many sodium go out and in?
3 sodium leave. So right here. So this is out, this is in. 3 sodium are leaving for every 2 potassium entering, and that costs 1 P of ATP to ADP. Michaela's also eating at this time, so that's great. Hopefully it's something that you enjoy. So we good with the sodium-potassium pump? How do the leak channels work with voltage channels? I heard you say something in the recorded lecture. How do leak channels work with the voltage channels? The leak channels are just there. Voltage gated channels are just ones that they're active. So they're ones that are going to respond to voltage. Maybe fall. I don't know if that answers your question, Joseph, but they're just two separate different types of channels. So I don't know specifically your question, but hold on to it. And then at the end of the lecture, once we're done this section, tell me if you still have that sort of question. But they don't work together then? No, so these, see, like they're not communicating with each other. Awesome. So when we are using the sodium potassium pump, and just like Michaela was asking, the number of ions that are sort of leaving and entering, it gives us a net negative charge inside of the neuron. So that gives us our electrical gradient. But because we're also pumping ions out and in, there's also a concentration gradient. Like there's more sodium outside of the cell and more potassium inside the cell. Yes. The leak channels are there for not just the sodium and potassium, but for everything, just to act as a buffer. Because your body doesn't, because remember, a membrane is separating outside from inside. So if you have too much inside or too much outside, you want to make sure that like there is sort of a safeguard just to act as a buffer. So it's through the development of this change in the ions that we get a electrical and concentration gradient. This is our resting membrane potential. Does that make sense, everyone? Clarify that question, Shane? Or it could be a statement. Ions and ATP are just ions. Well, no, because the ATP is already inside of the cell. Yeah. And the P is phosphate, not potassium for them, yeah. Wait, if leak channels, because they're very small, so they can only allow in a certain, like at a certain rate. The rate is so small. Think about the size of the holes. The leak channel hole is so much smaller than these like active channels. Think about a hose that's filled with water, and to stop, like, let's say the hose is always on, and then you poke like some needle holes in it. The water's still going to go through the hose, but then there's going to be some small amount of water that's spilling out. Yeah. Yeah. This is just showing how, because of the sort of unequal distribution of the ions, we get a negative charge. So Shane was calculating it in A&P. What is the resting membrane potential of the neuron, if you remember? Ooh, nice. Yep, negative 70. You guys are all nerds. I like nerds. Oh my God, I'm a nerd. Nice shirt, though. So are we all okay with the sodium potassium pump? What if it drops negative 70? But when it drops, yes, that's correct. I love how Joseph is just always 3 slides ahead. Do you plan this? Because respect if you do. Nice. You know what the difference between success and failure is? A plan. Yo, it's gonna be my 4th career. So you were all talking about like depolarizing now. Are you familiar with the terms depolarization and hyperpolarization? because it's not so much based on like whether it's positive or negative. In the case of the neuron, we all agreed that we had a negative 70 millivolt charge. That's the amount of charge. So if it is to depolarize, we're going to lose the charge. So in this case, that negative 70 is going to go closer to 0. If it was positive 70, a depolarization would it be losing charge and going closer to 0 again. Hyperpolarization is when you have an adding to the electrical potential or electrical charge that's already there. So if our resting membrane potential is minus 70, if we go to minus 55 millivolts, like Joseph was asking, would that be depolarization or hyperpolarization? Yep. And then if we were negative 100, would that be hyperpolarization or depolarization? Right. So that, and I think every year students get a little bit confused with that because we're used to D meaning negative or less, and then hyper meaning more, positive. It's not. It's about the charge. But not really. I don't think so, Michaela. It sounds, one thing that's good is I think it sounds like you are all really familiar with this portion of the lecture as well, which is great. Yep, Karen's correct too. So increase in charge is hyper, decrease in charge is D. And the reason why we need the buffering of, or the ability to change the charge in the neuron is because of this fact. Yes, you would have to know that. The threshold is negative 70, negative 55, yeah. The other number would be minus 70. Yeah. So what is one thing, and we're skipping ahead, so Joseph is going to know this question, is an action potential an all or none response? Which is a problem because we need the ability to, if everything's all or none in terms of a response, we wouldn't be able to like decrease our reactions. We wouldn't be able to go half speed at certain things. Everything would be fully yes or fully no in a way, right? On or off. And that's not really the way that our body works. The action potential is an all or none response. And so the way that we grade whether or not an action potential can occur is through what's called modulation. If you make the resting membrane potential hyperpolarized, that means that it's harder to get to the threshold voltage of negative 55. So let's say we had our resting membrane potential of minus 70. What happens if we made that resting membrane potential minus 80? Is it hyperpolarized or depolarized? So it makes a action potential less likely. And I'm not sure who said it, but someone was talking about local potentials. It means that there has to be, we're going to talk about local potentials next, but there has to be more local potentials, more stimulus to get that neuron to fire. And that's the way that your body is able to summate or sort of regulate the sensitivity of itself. An action potential needs to be negative 55 to occur because that's what the voltage gated channels, that's what they're responsive to. That's why. So that process of hyperpolarizing or depolarizing the resting membrane potential is called modulating, because you're modulating whether or not you want the neuron to be more likely or less likely to fire. Does that make sense, everyone? Oh, wait, sorry, Jason. I thought in order to make an action potential, it has to have more potential than threshold. No, the threshold is minus 55. So think of like your resting membrane potential as minus 70. Every local potential is going to take it down a little bit until it finally gets to minus 55. Then the voltage channels start, and then the action potential occurs. Justin's saying something. Can you define the word summation? Adding. Yeah, this is all going to be like the next 8 slides, Hannah. Madison. Yeah, that's right, Hannah. The inhibitory and excitatory info, or what do you mean? We have a question from Madison. The inhibitory and excitatory info. Oh, yes. Yeah, that's correct. Yep. Yep. So then that's what we're going to go into right now, right? So if the action potential is the all or none response, the input is the dendrites. So Shane, sensory neurons or what? Okay. Everyone else? What about motor interneurons? Great. We really did it. And so based on Madison's point, the dendrites are then going to be summating or adding up all of the stimulants, because some of them are going to be excitatory, some of them are going to be inhibitory. All those local potentials that are smaller on the dendrites are going to add up, because some of them are going to be negative, some of them are going to be positive. And then depending on how much of each there are, it will take our resting membrane potential from -70 to hopefully -55, and then we get an action potential. Now I just have to study everything else. Today's drinking game was action potential. No, I don't know, what have I said the most? Potential. So do we all understand the concept of these local potentials? They're going to occur as a result of stimulus at the dendrites. So either modality gated channels or ligand gated channels. These local channels, because it's these local potentials, just because it's one channel, it's just a small change, because when they open, they're going to allow in an ion, either positive or negative, depending if they're excitatory or inhibitory, but it's just a small amount of charge. And once you get a bunch of them, then you could potentially get an action potential firing. One thing about, you may see this definition in the textbook, local receptor potentials are when they are at the receptors of the sensory neuron. So these is another way to say modality gated channels. Receptor, because receptor means the beginning, this sensory receptor. Synapse is when you have one neuron attaching to another. So another way to say modality gated, ligand gated channel potentials is saying local synaptic potentials. So modality gated channels generate local receptor potentials, because that's where they are, sensory neurons. And then ligand gated channels generate local synaptic potentials. These only spread a short distance, whereas their action potential is an all or none response. And once it begins at the beginning of the axon, it will continue without stopping as it progresses all the way down or distally to the presynaptic terminals. Yep. Because the synapse happens at the end. So the synapse is, so the action potential will go to the end of the neuron at the presynaptic terminals. The presynaptic terminals then release neurotransmitters, and then those would go to the ligand gated channels of the next neuron, and that's why we have, that's why they're called synaptic potentials. So Joseph, they can either be at the same time or further apart. It all depends on, if let's say they're further apart, there's less of a summation. Yeah. Except for one thing, so Talassi is saying, so ligand would be the last step. She's correct, but know that it's never just two neurons. It's the first one's sensory, and then there's so many more synapses. So it's like ligand over and over and over and over and over again. the majority of them are ligand-gated channels. It would be the sensory receptors that are modality. So instead of saying ligand is the last step, it's all the steps except the modality ones are the first step. That's the way that I would say, think of it. So Joseph, you're all asking about temporal and spatial summation. Yes, that's correct. So the two ways that these local potentials that we're discussing can summate or add up is through temporal summation, through time. Spatial summation is through space. So let's look at what that means. Here we have, let's say this is the somas. Let's say these are all the dendrites. Do you want this to be a sensory or a motor neuron, Joseph? Anyone? Say sensory or motor. Motor, okay. So then if this is a motor neuron, these would all be ligand-gated channels on the dendrites. Here we have what would look like if we had one ligand binding to a channel and then causing a change in charge. See how we have our negative 70 millivolts resting membrane potential? One local potential only generated that much of a change. But what happens if we have the three signals in succession? So you have one ligand, another ligand, and then another ligand in time. See how there's a bigger change? That change in charge is added up. Paul, that's actually a great analogy. So then this would be a bunch of punches in one spot, or a bunch of punches. This is spatial summation. So instead of time, this is all local potentials happening all over at one time. So multiple in one spot, multiple at the same time, but in different locations. And you see that there's also a bigger change in the resting membrane potential. So the way that your neurons actually work is that you have spatial and temporal summation occurring at all times, where each punch is either positive or negative. And so it's that adding up of all of the different charges happening at once. If there's enough stimulus to depolarize the resting membrane potential up to negative 55, then we get an action potential. So our neurons aren't brains, but it's through this process of summation that we're able to sort of regulate or summate or integrate information. So Shane's asking, this is temporal on the right, yeah, and then spatial is on the bottom, yeah. Does that make sense, everyone? Awesome. I was just trying to make it sort of as easy to understand and at the level at which I want you to understand it for everyone. And then Talassi, remember how you were talking about, so the first in line, second in line, where ligand is the last step? Here we have like this, a way to think about it. See how the ligand channels happen each time there's another neuron? The first step is the modality-gated receptor. So Joseph is asking, and then what happens? Neurotransmitters packages it down at the same time. The neurotransmitters are always at the end. They're always being packaged. They're being released from the presynaptic terminals. Tatiana is asking, so the goal of summation is to get to the threshold in order for a fire signal? Yes, that's correct. Technically, the goal of summation is to summate multiple signals at once. Because remember, our brains aren't like, okay, well, should I fire now? Should I not fire now? It's just a whole bunch of stimulus. And then through the idea of local potential summating, we're able to integrate information. Because we don't want our neurons to fire if we don't want them to. That makes no sense. It would be ideal to have our neurons fire when we want them to, not haphazardly. Yes, Joseph, they're all just waiting. Talassi, do you like this diagram? Sort of explains your point. So when we get enough summation, everyone, like Tatiana was saying, the goal would be to potentially get enough of a change in our resting membrane potential to get that potential up to, or depolarize it up to minus 55 millivolts. And at which time, then we get our action potential. And that is an all-in-one response. As soon as it occurs, it will go from start to finish. And it's through the use of our voltage gated channels, which we've talked about the least just now. But it's through these channels that we get our action potential. So like we said, the threshold stimulus is minus 55 volts. That's a 15 millivolt change in our resting membrane potential. And so I know Joseph is super pumped to see this slide. But what happens here, so here we have our resting membrane potential. Here is an axon. So we get a buildup of our local potentials where we get up to minus 55. At which point we get to minus 55, you guys, or everyone can't probably read what the, just because the screen is so small. But what happens here is that we have our sodium channels, our sodium voltage gated channels open at minus 55. And once they open, what happens? All of the buildup of the sodium outside positive enters the neuron, and then that's why we get such a big change in potential. Then halfway through, we get our potassium channels opening. And remember, we had pumped potassium in. The potassium leaves then against the concentration gradient, and then our resting membrane potential returns and actually overshoots a little bit. So when we were talking about absolute versus refractory times, this is why we can get that concept. I think it was Shane that brought it up. The absolute refractory period is going to be the point in which in time that we can't have another action potential. What really happens is that once we have a release of that energy, we need to build it back up again because it's based on the electrical potential. So the absolute refractory period is the amount of time before we can generate another action potential. And it's going to be based specifically on the sodium channels, the sodium voltage gated channels. The relative refractory period is the point in time where we have our sodium channels closed, but the potassium channels are open. So right here, where we have our resting membrane potential will probably be minus, I don't know, diagram minus 80. So it's hyperpolarized. So in a strong enough stimulus, we could get an action potential in this time. Does that make sense, everyone? Doesn't cross my fingers. Oh, I missed some questions. Did I miss a question? Just ask again. Will this be an example of a live question? No. Is everyone okay? I don't think I missed a question. Yeah. Can you explain the difference between absolute and relative again? Sure. The absolute refractory period is the point in time where you can't have an action potential again because the sodium channels, the voltage gated sodium channels are closed, or sorry, are not closed. So you can't have another action potential. The relative refractory period is where you could potentially have another action potential generated, but because the membrane is hyperpolarized, you just need a larger stimulus. So you could have another action potential generated with a large stimulus here. No matter how large the stimulus, you can't have another action potential in the absolute refractory period. It is absolutely think of it this way: it's absolutely not available. It's relatively unavailable. Yeah. Here's another diagram. Awesome. Oops. Madison's asking a question. During a relative refractory period, would you just need to increase the memory? Yes, same thing. The difference is just greater. Yes. So Madison's saying that you would still need to get to the special potential of -55 to get the sodium channel voltage channels to open. It's just a greater change. Yeah, that's perfect. So moving on from potentials, and I know you're probably really sad to see that part of the lecture end. Are we all familiar with saltatory conduction, or the nodes of Ranvier? So let me explain to you at the level of which I would want you to know. RV's saying he doesn't know. That's okay. Okay, so here we have a diagram depicting what the axon would look like in terms of channels. So the channels on the axon, obviously this is two-dimensional, but it's voltage-gated channel, voltage-gated channel, voltage-gated channel, like dominoes, end on end. So can we see that there would be channels in series? Okay, so what happens is all the local potential energy is summated here, and then eventually we get to -55. The first voltage-gated channel opens, and then the charge changes, and then the next one in the line fires, and then the next one, and then the next one. That's why it goes down the line like dominoes. Does that make sense? And that's why it's an all or none response. However, we can do something to speed up the flow of the energy. So if we had a hose, so think of this like water and hose example. If we had a hose, what would be one way to make the hose release more water? Think of like a fire hose versus a garden hose. I think Shane said that. Wider. So the bigger the neuron axon, the faster the conduction happens, just like water. The other way is myelination. This is what myelination would look like under a microscope. So we're going to learn about glial cells. Glial cells are support cells of the central nervous system. They're just not neurons. But here we have one cell that's going to generate myelin. Myelin is like the sort of rubber wiring, think of like a wire. It's like the rubber coating of our electrical wires. And why is that there? What does the rubber around protection insulation correct? So what that does is it helps keep the charge in. And the reason why it allows for faster, because it keeps the charge in, the reason why it allows for faster conduction velocity is through what's called the use of these nodes of Ranvier. So I don't know if you guys can like get real close to the screen, but do you remember in the old example, 3 slides ago, we had channel in quick succession. So channel, 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 channel. They were very like spaced together, or like very closely spaced together, sorry. By having myelin, because it holds in the charge, now look how further apart the channels are. So instead of having 100 dominoes to get from the beginning to the end, because of myelin separating the dominoes, you can now only have 10. So what's faster, 100 dominoes to knock over from start to finish, or 10? We all get Nobel Prizes. Shane thinks he's funny. Shane's still minus 55. Shane, guys, Shane has calculated his mark in the course. He still passed. And that process of the less dominoes, that's the process of saltatory conduction. And that's why it speeds up the flow of the action potential. Carlos says he loves the class. Well, we love him more. Okay. We're doing okay? Promise? Awesome. Hera doesn't believe in promises. She only believes in action. Good. Good. Good for you. Know your worth, girl. Okay. So, one thing that I wanted you guys to, who's stressing? You guys okay? About what part, Miguel? Sure. Yeah, that's good. For sure. And Jen's probably feeling the same way. It is a lot of info, but the best thing is to talk to me after class would be the best thing. But then know that when you go through the lecture again and again, it won't seem like a lot of info because we've really only touched on like 5 different things through the lecture. And then it's like topics around those. So you'll feel less overwhelmed. Do we all remember these terms here, afferent versus efferent? Which way does the potentials travel in afferent axons? Yep, and then efferent's the opposite. So sensory or motor? Sensory and then motor. Interneurons, technically, they can go whichever direction because they're in between, right? Now, if you considered like the number of neurons, for every 1 sensory neuron we have in our body, we have 10 motor neurons. We have 100,000 interneurons. The way that the nervous system works so well and is able to sort of process so much information is through the number of connections, all through interneurons, sending signals back and forth, back and forth. And so the interaction between neurons is not in that initial slide where it's like one sensory neuron goes to one motor neuron, and then it's never one, just one, just a one, just a one. It's always divided or converging signal. And so we can have multiple neurons influencing one neuron here. So this is a converging signal where we have multiple neurons converging on one neuron, right? This would be generating local potentials for an action potential. Diverging signal also occurs where we have the neuron sending its signal to multiple other neurons. And it's through this interaction that we have one signal being able to affect so many things throughout our body. Because the signals aren't just one-to-one, there's converging and diverging signals. Does that make sense? Well, it's all going to be based on shape. So Shane is asking, like, is this converging and diverging true of all neurons? It's based on their shape. So depending on, let me show you what, like, I don't know, do you remember the slide where what a motor neuron really looks like? It all depends on shape. So some of them are going to have multiple tails at the end. Some of them are going to look like this. All depends on shape. Karen is 10 slides ahead, so she's rivaling Joseph. Okay. Yeah, that's true. But Aaron, one thing about, you would think that the sensory is more converging and motor is more diverging. But think about when you get like, so let's say I pick up a hot pan, and then my body withdraws. Then I feel the pain. Then there's also diverging signals with sensory neurons. You got to go to multiple areas. Yeah. The term glia means the support cells of our central nervous system. So our central nervous system has different cells, and up to this point, we've talked about the neuron. The neuron is the most important in a sense because it is our functional unit of the central nervous system to send signals. And when I say central nervous system, I mean sensory, I mean central and peripheral. I mean the whole nervous system as one. The glial cells are our support cells, and they're divided up into two different categories. There's microglia and macroglia. Macro meaning large, micro meaning small, and they have different functions. The macroglial cells are classified into three groups. The first one are called astrocytes, and this is the most abundant cell in our human brain. Because what they do is they're called astrocytes because they look like stars, but they act as like the structure. They are like proteins and they hold everything together. So let me look on this slide. See how we have the astrocytes sort of connecting the neuron to, let's say in this case, a capillary. The astrocytes are basically like the protein structure. If you think of like a building, it's like the support structure holding everything together. Now, initially, when they looked under a microscope, they thought that they were just there for holding structure, but then they realized that the cells are living and then they can do lots of different things as well to help support the nervous system. They can send nutrients through each other. They can help in picking up neurotransmitters. They're involved in cell signaling. So they do other things. The main point that they are utilized for is structure. And that leaves us with the two other types of macroglial cells, which are the oligodendrocytes and the Schwann cells. And I know, again, probably Jen and Michaela are stressing out. It's just a lot of words. But the oligodendrocytes and Schwann cells are both utilized to produce myelin. And what is myelin used for? Right. Oligodendrocytes produce myelin for the neurons in the central nervous system. So that's with everything encased in bone. The Schwann cells are utilized to myelinate the neurons in the peripheral nervous system. So we have astrocytes and then the oligodendrocytes and Schwann cells that produce myelin. And those are the three classes of macroglial cells. They look a little bit different, so that's why they're named two different things. Karen, let's see if you remember, or anyone. What counts as the nervous structures in the central nervous system? I just said it 30 seconds ago, but just to review. In case of bone, yep. So then the peripheral nervous system is everything outside of the vertebral column and brain. The microglial cells act as, I don't know if you guys are familiar with this term, but the phagocytes are white blood cells of the central nervous system. So remember there was a blood-brain barrier in our bodies, so not the central nervous system. The main cell that's utilized for killing and removing bacteria and debris and inflammation is our white blood cells. Those white blood cells can't cross over our blood-brain barrier. So the central nervous system has its own, the nervous system has its own like white blood cells or cell that does phagocytosis, which is eating. It's called the microglial cells. Yeah, yes, that's true. Fair is the word, Lyman. And so the reason why I'm bringing up the microglial cells, because I want to put a clinical spin on it for everyone just before we finish off this lecture. A lot of diseases are in response to an over stimulated process of inflammation or these microglial cells in the central nervous system. So we have inflammation in the body, and that is dealt with in a lot of different ways, but with white blood cells. In the nervous system, we have our microglial cells that are involved with neuroinflammation. Anything that's in the slides, Joseph, is fair game. And so you read ahead. So how many diseases are there in the slides coming up? 2. So yeah. So yes, you would need to know the 2, Joseph, which because you're so far ahead, I bet you probably already know 5. So can we all agree that inflammation is a good process, right? Okay, but depends, because it can, if it's too much, it's bad, right? To a point, and we're all agreeing on the same thing. It's the same thing with neuroinflammation, or the inflammation of the central nervous system or nervous system involving the microglial cells. It's beneficial because it is an intervention to help heal or remove bacteria or any injury that's gotten into the nervous system. But the problem is that if it's too much, it can now cause death and decay of the nervous system or degeneration. And this is what happens in a lot of the neurological diseases that we're going to look at. And Joseph is going to remember them. Here we have a hypothetical picture of neuroinflammation. So here we have our neurons, and they're not very happy right now. They got all kind of bacteria all around them. And then the microglia comes in and is like, I got this. And now it's eating up all of these bacteria. It does look like Fruity Pebbles. Has anyone ever heard of the term of peripheral neuropathy? Like carpal tunnel, sciatica, what else? Give me other examples. This compartment syndrome. Impingements, yeah, any nerve impingement. No, it would be just so that ALS is more central. Any impingement, the reason why that happens is the nerve doesn't stop working completely, it just loses its myelin. And so what happened is that, you remember, the signal is important to go fast. When there's a loss of myelin, it slows down or interrupts the transfer of that electrical potential or action potential. So peripheral neuropathies are pathological loss of myelin. So it's not good. And that's what happens in a lot of our neurological diseases. The first one we're going to talk about is Guillain-Barré syndrome. Okay, those are diseases. I'll give you all credit for that. But the lupus is an autoimmune one, so that'll work. Fibromyalgia is it is a pain syndrome, so it's not this. And then diabetes is not this. Multiple sclerosis is also an autoimmune disease, but not just periphery. Yes. Oh, like a peripheral neuropathy. Yes, you're right. Sorry. Stenosis. Yep. Okay. Has anyone ever heard of Guillain-Barré syndrome? Now, this is important because, not getting political here, but Guillain-Barré syndrome has been in the news because it is said to be a reaction to vaccines. It is not just because of that. Guillain-Barré syndrome happens typically as a result of an intestinal infection. And then what happens is that your body develops antibodies for that infection, fights it, but then those antibodies, for whatever reason, start interacting with your own myelin in your peripheral nervous system. And then once the antibody attaches to the myelin, it's a marker for the microglia to attack it. And then so you get pathological demyelination of neurons. So I want to show you guys a TikTok. I'll look up TikToks for you guys about Guillain-Barré. Let's see. Uh-oh. Didn't find a good one. There you go.
Okay, so I got a lot of comments kind of asking like my story or what happened.
Can you see your face?
By the way, I don't think this is rude at all. Feel free to ask any questions. I actually enjoy sharing my story, and maybe there's someone out there that feels like they have no one to relate to who's going through this, because it's kind of rare. So yeah, anyways, it started December 2017, And I woke up one day and realized I couldn't move my face. I was trying to do my makeup and I couldn't pucker my lips. I couldn't smile. I still have facial paralysis. So like, that's me trying to smile. It's just not all the way back yet.
So Shaw, Bell's palsy is
so I
when
went
it affects
to a
just the
walk-in
facial nerve.
clinic and they misdiagnosed me with Bell's palsy. And they sent me home with some sort of antibiotic. I think it was prednisone or something. And then the next day I tried to swallow water. I couldn't even swallow water, let alone take the pill. It was pretty big. And so then I went to the ER, waited there for 6 hours. The triage nurses tried to send me home after watching me attempt to drink a cup of water, which spilled all over my face. And they had the audacity to tell me, well, you got some of it down. And I knew something was wrong. At this point, I'm having a really hard time breathing. I can't walk. I'm tingly all over. So then I finally get back to a room. At this point, I'm passed out. They have me on all sorts of medications. They did a spinal tap on me and realized something was really wrong. They didn't have the diagnosis yet. I live in a really small town, so we don't have the best hospital here. So I was actually airlifted to San Francisco to be in better care. And this whole time I'm intubated, I'm in a coma.
Yes,
I don't
that's
remember
correct,
anything. So this is all stuff that my family has told me. And I get to San Francisco. They diagnosed me with Guillain-Barré syndrome. And then they started doing the treatment. So that is like plasmapheresis and blood transfusions, things like that.
Oh.
And then
So the syndrome itself is an autoimmune reaction attack. So that's you're attacking your own myelin, and then you're stopping the proper functioning of neurons wherever that's happening. So it can happen all over. She had it in her face. You can have it in the limb muscles sometimes. And then like any disease, some people get it a lot and some people get it like it's a spectrum. Some people get it not as much. Yes, and so with autoimmune diseases, it's always the antibodies that cross-react. So antibodies, your body's immune system creates antibodies to recognize things that it should attack. And for whatever reason in autoimmune diseases, I can talk about it after the class if you guys really want, but what happens is that attaches to the myelin and your body attacks it. Yeah, so anything that would cause an immune reaction. So that's why there's a lot of different reasons why it could happen. So like an intestinal infection, or with the vaccines, you're saying because you're creating antibodies, or a virus infection, or anything. Yeah. And so obviously this is obscure, but this is why you get these symptoms here. The way to treat it is through plasmapheresis, and that's where you are filtering the blood from those antibodies. The antibodies are what's causing it, so if you get rid of them, then that's not a problem. Intravenous immunoglobulin therapy is when you inject a drug that will bind to those antibodies. And so in effect, making them non-functional. And then the last one, of the two diseases that we're going to talk about, the next one is multiple sclerosis. What would COVID causing loss of taste be? Ooh, so that is because it's hitting, oh wow. Wait, what are you guys saying? You guys are answering Joseph? Can I make a joke? COVID's not real, just kidding. So because it attacks like the mucosal membranes, so it's the areas where we smell and taste. That's not an autoimmune disease though. I think Joseph's just trying to show off. Multiple sclerosis is an autoimmune disease, but this is now not affecting the peripheral nerves. This is affecting centrally. So we have in our immune system that is producing antibodies that attack the oligodendrocytes. So remember, in our central nervous system. And then what happens is that we get these white plaques in our brain. And that's how the discode is. It's multiple sclerotic plaques in the brain is a sign that you have multiple sclerosis. Clinically, what happens is it typically happens in women over the age of 40, and they get these relapsing, remitting episodes of different neurological symptoms. And then they go through periods of where it's active, and then it'll stop. So will lose feeling in their hand, and it'll stop. And then they won't be able to see out of their right eye 6 months later. And then those periods of, typically in relapsing remitting, which is the most common multiple sclerosis, those periods get closer and closer together. So the topic of the tutorial that won't be on this midterm is about multiple sclerosis. In terms of, and multiple sclerosis is super common, that's why I brought it up, but it's an autoimmune disease. And in this case, it is antibodies cross-reacting with the oligodendrocytes, which is myelin in the central nervous system. And then we have our microglia eating that up, and it's leading to bad neuroinflammation. This is what's giving us our symptoms. And so if anyone knows, and we all do, someone with multiple sclerosis, that's why we get those symptoms. Physical rehab helps for those individuals because you're doing repetition of trying to use the neurons that are still there. And there's lots of other types of reasons. People think vitamin D helps, for example. The medication they take are typically anti-inflammatories. Yeah, there you go. Awesome. So that is the end of the lecture. For those of you still watching the video, make sure that you check the announcement for the breakdown of the midterm. And it's going to be all through Canvas, and will require Respondus Respondus Monitor to do the test. I'm just going to stop recording. No. Everyone, it's froze. It froze at the very last second.